Hello, and thanks for joining us on our training series on A to D and D to A sampling theory. My name is Roger Hosking, and today we're going to be covering several topics. We're going to be looking at A to D and D to A converters. We're going to look at the time domain and the frequency domain views of aliasing, a term many of you have heard about. We're also going to review the Nyquist sampling theorem and introduce a convenient fan-fold paper aliasing tool to help you evaluate aliasing issues. Then we're going to look at baseband sampling and then undersampling. So let's start with what is a sampled data system. A sampled data system involves usually an A to D converter that takes periodic voltage measurements of an analog signal. The A to D digital samples represent the sequential voltage readings that it makes. A D to A converter generates an analog output voltage based on the digital samples that are delivered to it. The sample clock determines the rate of A to D conversion or the rate of D to A conversion. One conversion occurs each sample clock. So let's take a look at a sine wave signal at 10 megahertz. We're going to feed this into an A to D converter, and we're going to notice that the sine wave has a period of 100 nanoseconds. That's one cycle of the sine wave. Let's choose a sampling rate of 40 megahertz, which has a sampling interval of 25 nanoseconds, or 1/4 the period of the sine wave. The vertical lines represent the times that the A to D converter will do the A to D conversion. These are the sampling periods. And notice there are 4 sampling periods within one cycle of the sine wave. So at each time the A to D converter converts the number, it creates a digital value. These values are shown, and these are the sequence of numbers that are delivered out of the A to D converter that we just looked at before. Let's take a look at the D to A converter operation. The D to A converter produces an analog output voltage in steps that are represented by the value of the digital inputs. So in this case, for a sampling rate of 40 megahertz, we see the samples that were created by the A to D converter being delivered as DC voltage outputs from the output of the D to A converter. In fact, the signal, the analog signal, contains the original 10 megahertz sine wave that was originally sampled. Let's now shift the frequency to an input of 30 megahertz. Here's a 30 megahertz input sine wave. We're going to sample at our same 40 megahertz rate, 40 megasamples per second. You can see the samples that are generated at each sampling interval look familiar. In fact, these are the same samples that we got when we had a 10 megahertz input. So now you begin to see what's happening. In case of the output, we are generating those same samples at the output, and in fact, the output signal does contain a 30 megahertz output waveform with the same samples as those for the 10 megahertz output. Let's go up a little bit higher in frequency. Let's put in an input signal of 50 megahertz. In this case, with a sampling rate of 40 megahertz, the sampling periods are shown, and the digital samples created, again, are exactly the same as the samples that we had from a 10 megahertz input. And with the D to A output, that same sample sequence contains samples that deliver a component of 50 megahertz output in the analog output of the A to D converter. So you can see there's a little bit of confusion. What do those samples that we see really represent? A 30 megahertz, a 50 megahertz, or a 10 megahertz signal? Let's superimpose all 3 frequency signals on the same graph. Here's our 10 megahertz signal. Here's our 30 megahertz signal in green. And here's our 50 megahertz signal in black. The digital samples that we created are exactly the same for all 3 waveforms. You can't tell the actual input frequency simply by looking at the samples. Thus, the 30 megahertz and the 50 megahertz signals have become aliased to 10 megahertz. That's where the term came from. Alias means a false name. Let's take a look at the frequency domain view of aliasing. Here's a graph where we're plotting frequency of the input signal along the horizontal axis. We have a 10 megahertz input, and that gets faithfully represented as 10 megahertz. But if we have a 30 megahertz signal shown here in green, that effectively gets aliased down to 10 megahertz. In other words, we can't tell it apart from a 10 megahertz signal. And likewise, with a 50 megahertz signal at the input, that signal gets aliased again down to 10 megahertz, and we can't distinguish it from either the 30 or the 10 megahertz signal. So you're beginning to see what aliasing is, both in the time and the frequency domain. And if you think about it, aliasing just makes sense. The more closely you want to monitor behavior, the more often you need to take a look. For example, if you have a stock portfolio, you could look at your stock portfolio once an hour or once a year. The more often you look, the better you can see sudden, important changes. Another example would be the digital speedometer on your car. Many cars have digital readouts for the car's speed. But what if the number changed only once every minute? That wouldn't be very convenient. At such a low sample rate, that is one reading per minute, you might get quite a few speeding tickets. The digital readout on the speedometer is nothing more than an A to D converter that's converting the analog rotational speed of a gear in your engine to the rate of travel of your car. Now let's take a look at the Nyquist sampling theorem. This is very important and one of the most fundamental theorems in sample data. Nyquist sampling theorem says that the sampling rate must be at least twice the bandwidth of the input signal. In our previous examples, half of the 40 megahertz sampling rate that we use as an example is 20 megahertz. The 10 megahertz signal was below that 20 megahertz limit, so no aliasing occurred. However, the 30 megahertz and the 50 megahertz signals we tried were above the half sample rate, or above 20 megahertz, and they were aliased. Later we'll see why the theorem uses the term bandwidth instead of frequency, but you can see that the Nyquist theorem correctly represented the problems that we had in the earlier waveforms that we were digitizing. Now let's take a look at the fan-fold paper aliasing tool. This is a convenient tool that allows you to see aliasing problems and scenarios. In order to visualize sampling, imagine that you have a stack of fan-fold computer paper, like the type of paper that used to be in a box feeding a line printer. Except imagine that this fan-fold computer paper is transparent. You can see completely through it. We're going to use the horizontal edge of the paper as the frequency axis. We're going to scale the frequency axis so that the paper folds line up with multiples of 1/2 the sampling rate. Starting on the left, you can see the first fold outward is at 1/2 of the sampling rate. The next fold, the backward fold, is at the sampling rate. And the third fold is at 3/2 of the sampling rate. Each sheet of paper that you see here represents a Nyquist zone, starting with zone 1 over at the left. Now we're going to use the vertical axis of the fan-fold paper for signal energy at the input. So we plot the frequency spectrum of the signal to be sampled on our fan-fold paper. Now to see the effects of sampling at sampling rate fs, what you need to do is collapse the transparent fanfold paper into a single stack. And here's what it looks like. The effective resulting spectrum after sampling is seen by holding this transparent stack up to a light and looking through the stack. What you see is that all of the Nyquist zones, that is, all of the pages of the fanfold paper, have been superimposed upon each other. All the signals are, as we say, folded or aliased, and they can't be separated after the sampling. So you can see that by looking at this mess in the folded image, you can't tell which page or which Nyquist zone any of those signals in red came from. And that's the problem with aliasing. Once aliasing occurs, the data is destroyed forever. So it's really important to sample data correctly and to avoid aliasing, or to do it in a very responsible way. So let's see, for example, how aliasing looks for a signal that's increasing from 0. And in order to do this experiment, it gives you a really good feel for how this works. So we're going to connect a signal generator to an A to D converter. And we're going to start off with the signal generator at 0 Hertz. That's represented by a red line over there on the left of our plot. Now we're going to look at the digitized spectrum after the A to D converter, after the aliasing and after the folding of all of these zones down onto one sheet between 0 and fs over 2. Now we're going to start turning the knob on the frequency generator and increase the frequency from 0, and first we're going to increase it up to fs over 2. Notice that in that first page, after the A to D signal moves also from 0 to fs over 2. But now, as we move through zone 2 in our frequencies, we turn the generator up higher, what happens is the resulting folded image actually moves back to 0. So a signal coming in at fs looks, after the digitizing, after the A to D converter, looks like it's at 0. As we go higher in frequency, up to 3 fs over 2, the resulting image goes from 0 to plus fs over 2. And again, another page, we move back to 0 at 2 fs. We move up to fs over 2 during zone 5, and for zone 6, we go back to 0. So that at every multiple of the sampling rate, you'll notice the resulting spectrum is at 0, and for all of the odd multiples of the half sampling rate, the resulting spectrum is at fs over 2. So you can see that aliasing folds the signal forward in the odd zones and backwards in the even zones. Now let's take a look at baseband sampling. Baseband sampling defines all signal energy must be within the first Nyquist zone. When this is true, we call this type of sampling baseband sampling. So we have a signal shown in zone 1. This rule for baseband sampling can be met in two different ways. We can insert a low-pass filter to eliminate all the signals above fs over 2. This kind of filter is often called an anti-aliasing filter because it removes all the signal energy in zones 2 and higher. We could also increase the sampling rate of the A to D converter so that all of the signals fall below fs over 2. But high-speed A to D converters get more expensive and typically result in fewer bits of resolution. When you collapse the fanfold paper in baseband sampling, the image in zone 1 is preserved, and none of the other pages or zones fall on top of it because all of the energy has been removed. The only energy that we had was in zone 1, so even though folding occurs, you're guaranteed not to get any interfering signals because the other zones were clear of signals that could otherwise fold. Let's take an example of baseband sampling. Suppose our customer has a signal in the frequency range of 10 to 40 megahertz. Since the highest frequency is 40 megahertz, let's choose a sample rate that's at least greater than twice 40 megahertz. PENTEK offers several A to D converter products with sample rates of 100 megahertz. So let's create a fan-fold paper plot scaled for Fs equals 100. You can see the paper there with the half sample rate at 50 megahertz as the fold in the middle. Now let's plot the input signal. You can see the signal extends from 10 megahertz up to 40 megahertz. And as the baseband sampling rule says, all of the signal energy falls within zone 1, fully compliant with baseband sampling, so this is a valid baseband sampling scenario. Now let's talk a little about undersampling. In undersampling, the rule is that all signals must fall within a single Nyquist zone only. Here we see a signal in zone 4 and no other energy in zones below or above zone 4. This can be done in two ways. You can insert a bandpass filter to eliminate all signals outside of the one Nyquist zone your signal is in. This is often done by an IF filter, for example, in a communications receiver. The bandpass filter is actually part of the receiver, and this is an extremely popular use for undersampling. Another way is to adjust the sample rate so all signals fall within the Nyquist zone. Again, back to the IF signal. For example, if your IF frequency is 70 megahertz and it's 10 megahertz wide, it would fall in the second Nyquist zone for a signal sampled at 100 megahertz. The fold is at 50, and the range from 50 to 100 entirely contains a 10 megahertz signal centered at 70. Let's see, after we fold the fan-fold paper, collapse it into one stack and look through it, you can see that zone 4 is the only zone that had energy, and so the input bandpass signal is correctly preserved after the sampling. The benefit of undersampling is really quite remarkable. First of all, baseband sampling requires the sample rate to be at least twice the signal frequency. Nyquist theorem says that the sampling rate must be twice the signal bandwidth, not frequency. So, undersampling takes advantage of the Nyquist's bandwidth rule. Undersampling allows us to have a lower A to D sample rate even though the signal frequency is high, provided that the entire signal bandwidth is limited. That's the but. The benefit, if you can achieve this, is that it allows you to use a lower frequency A to D converter than otherwise. For example, if you had to use an A to D converter that was twice the frequency of the signal in zone 4, you would have to use a signal that would be up at perhaps 4 or 5 times higher than Fs. So it could be a much more expensive, a larger, and a lower resolution A to D converter. So let's summarize what we've learned today. First of all, aliasing occurs when an A to D or D to A sample rate is less than twice the signal frequency. And when aliasing occurs, the resulting samples are the same as the samples for non-alias signals, hence the term alias. Once A to D aliasing occurs, there's no way to know what the input frequency truly was. Nyquist's theorem tells us that sampling rate must be at least twice the bandwidth of the signal. We looked at the fanfold paper aliasing tool. This is extremely useful for doing a aliasing analysis. For baseband sampling, the rule is that all input signals must be within the first Nyquist zone, that is less than the sample rate divided by 2. For undersampling, all input signals must fall within only one Nyquist zone. Undersampling is intelligent aliasing, that is, aliasing by design, carefully chosen sampling rates, carefully chosen center frequencies and bandwidths so that all of the energy lies within a single Nyquist zone. This can result in lower speed A to D converters than you would otherwise use in a baseband. Thank you for joining us today, and we hope this was informative. There will be additional seminars that will cover software radio topics coming up soon. Thanks again.